There is a wooden top on a table. Someone has given it a spin, a child, maybe, or someone who picked it up without thinking, and now it turns. It moves in a tight, wobbling circle, and for a moment it is perfectly upright, humming against the wood, and then the hum deepens, and the wobble widens, and it slows, and lists, and falls. You have watched something like this your whole life. It feels like an ending. The spin runs out, the top stops, but here is what is actually happening. The top is not losing its spin to nothing. Angular momentum does not disappear. It transfers through friction, through the surface, into the table, into the floor, into the building. Somewhere in the vibrations of everything the top touches, the rotation is still there, dispersed past the point of recovery. Nothing was lost. It moved, and that is the thing that stays with you when you sit with it long enough. The spin in that top, the spin in the ice skater who pulls her arms in and accelerates without anyone pushing her, the spin in the planet you are lying on right now, the spin in the solar system carrying you around the galactic center at 828,000 kilometers per hour. All of it traces back, through an unbroken chain of conservation, to an early universe that was never quite smooth enough to be still. Almost everything in the universe turns for the same reason. None of it can stop. Hello, and welcome to Sidereal. Tonight we are going to spend some time with rotation, why the universe spins, why everything in it spins, and why you are part of the answer. If this kind of slow, unhurried exploration is useful to you for sleep or winding down, a like or a subscription genuinely helps this channel keep going. And I am curious where you are listening from. Drop your location and time in the comments if you feel like it. Here is the question tonight will follow. Conservation of angular momentum tells us that spin, once present, persists. It cannot be destroyed. It can only be transferred. But the law says nothing about where spin came from in the first place. If you want to explain why everything rotates, you eventually have to explain where the rotation entered the universe to begin with. By the time we reach the end of this, you will understand not just why things spin, but why the universe was never in a position to be still. Let's begin. Think about what a spinning top is actually doing. It is an object rotating about an axis, a mass distributed around a center, turning at some rate. If you leave it alone, if nothing touches it, it keeps turning at exactly that rate. Not approximately. Exactly. This is not an idealization or a rounding convention. It is a law conservation of angular momentum, and it holds as precisely as any law in physics. The quantity being conserved is called angular momentum. It is the rotational equivalent of ordinary momentum, the tendency of a moving object to keep moving. For a rotating object, it is the product of two things. One is the moment of inertia, a measure of how the object's mass is distributed around its axis of rotation. An object with mass concentrated near the axis has a small moment of inertia. An object with mass spread far from the axis has a large one. The other is angular velocity, how fast the object is rotating. The product of these two quantities is angular momentum, and in the absence of an external torque, that product stays the same. This is why the figure skater spins the way she does. She begins her rotation with her arms extended, mass distributed far from her axis, moment of inertia high, rotation relatively slow, then she pulls her arms in, mass moves closer to the axis, moment of inertia decreases, and because the product must remain constant, angular velocity has to increase. She accelerates, not because anyone pushed her, not because new energy entered the system from outside, purely because she redistributed her mass. The spin was always there. The geometry changed. The falling top is the same story from the other direction. It is not losing angular momentum to nothing. It is transferring it to the table through friction, to the floor through the table, outward into everything the vibration touches. If you could track every molecule that absorbed a piece of the top's rotation, if you added them all up, you would find the original angular momentum accounted for. Exactly. Dispersed. Yes. Unrecoverable in any practical sense, yes. But not gone. This might seem like a fine point, but it matters enormously, because it means that angular momentum is not generated or destroyed by ordinary physical processes. It moves. It amplifies when mass collapses inward. It disperses when things spread out. But the total, in a closed system, is fixed. It is worth pausing on why this should be true at all. Because the answer is one of the most beautiful results in physics, and it is not obvious. Conservation laws can feel like accounting rules handed down from nowhere, quantities that simply happen to stay constant, for no deeper reason than that they do. They are not. In 1915, the German mathematician Immanuel proved a theorem that ties every conservation law to a symmetry of nature, and the connection is exact. Where there is a symmetry, a way the world can be shifted or turned without changing the physics, there is a conserved quantity, and where there is a conserved quantity, there is a symmetry behind it. The case of angular momentum is the cleanest example there is. The symmetry it corresponds to is the rotational symmetry of space itself, the fact that the laws of physics are the same in every direction. An experiment performed facing north gives the same result as the same experiment performed facing east. Space has no preferred orientation. Turn the whole apparatus, and nature does not notice. Noether's theorem says that this single fact that direction does not matter to the laws is the reason angular momentum is conserved. The persistence of the spinning top, the acceleration of the skater, the rotation of the galaxy, all of it follows from the emptiness of space having no built-in sense of which way is which. Noether arrived at this in difficult circumstances. She was, at the time, one of the finest mathematicians in Europe, and she was barred from holding a proper professorship because she was a woman. For years she lectured under a colleague's name, unpaid. The theorem she proved in that period turned out to be one of the load-bearing results of all of modern physics. It is the reason physicists, when they find a quantity that is conserved, immediately go looking for the symmetry behind it, and the reason they trust that the law will hold not just here and now, but everywhere and always. The conservation of angular momentum is not a local convenience. It is woven into the structure of space. This is why the bookkeeping is so absolute, and why every chain in this story holds. When the gas cloud collapses and spins faster, when the skater pulls in her arms, when the neutron star winds up to a fraction of the speed of light, the total angular momentum does not merely tend to stay the same. It stays the same because space has no preferred direction, and that is as deep a fact as physics has. The spin has nowhere to leak away to, because there is no direction it could prefer to leak toward. Now consider what this implies for a collapsing gas cloud. The solar system formed from a cloud of gas and dust approximately 4.5 billion years ago. That cloud was not static. Nothing at this scale is perfectly static. There are always small, random motions, the result of the cloud's own turbulence and the gravitational tugs of neighboring structures. These random motions across a cloud hundreds of thousands of times larger than the eventual solar system had a tiny net angular momentum. The motions did not perfectly cancel. There was a slight excess of rotation in one direction. When gravity pulled the cloud inward, that net rotation had nowhere to go but be conserved. The cloud shrank, the moment of inertia dropped, the angular velocity rose. And here the arithmetic matters, because it is the same arithmetic that will return several times tonight at larger and smaller scales. The moment of inertia of a collapsing cloud falls roughly with the square of its radius. So as the cloud's radius dropped by a factor of something like 100,000, its rotation rate did not climb by that same factor. It climbed by something closer to its square. A cloud that started with a rotation too faint to detect with any instrument of that era ended as a disk spinning fast enough to throw off planets. This is also why the solar system is flat, not because something pressed it flat, not because of any particular property of the sun or the planets, but because of the geometry of angular momentum conservation under gravity. As the cloud collapsed, the rotation resisted the inward fall in the direction perpendicular to the spin-axis material that was held up, partly by its own circular motion. But along the rotation axis itself, parallel to it, there was nothing to resist the collapse. Material fell freely in that direction. The result was a disk, flat in the plane of rotation, concentrated at the center. Saturn's rings are flat for the same reason. So is the Milky Way. So is the accretion disk that forms around a neutron star or a black hole when matter spirals in. The shape is not a coincidence or a design. It is the only shape a rotating, collapsing structure can take. But there is something the law of conservation cannot tell you. It can tell you that whatever spin was present in the original cloud was preserved and amplified during collapse. It cannot tell you where that spin came from. The law conserves what was already there. It does not explain how it got there. For that, you need a different question, and the answer to that question will take most of tonight. For now, the thing to hold is this: the solar system's spin, the disk shape, the direction all the planets orbit, the direction most of them rotate, all of it traces back to a tiny asymmetry in the motions of a gas cloud that existed before the Sunday. The Sun is 4.5 billion years old. The rotation that produced it is older still, and the chain does not end at the gas cloud. The question of where spin originally came from is older than the solar system. But before we follow it backward, there is something closer to consider. Something about spin that is stranger than angular momentum conservation, stranger than collapsing clouds, because it operates at the level of the particles themselves, and it cannot be explained as anything turning at all. The physics teacher's answer to why things spin is conservation of angular momentum. It is correct, but it is the answer to the second question, not the first. The first question is, why was there any rotation to conserve? A perfectly smooth early universe, one where matter was distributed with exact uniformity, where every motion had an equal and opposite motion to cancel, it would produce nothing that rotated. In principle, if the starting conditions had been perfectly symmetrical, there would be no spin anywhere. The law of conservation would faithfully conserve a total angular momentum of zero. You would have a universe expanding uniformly outward, matter spreading evenly in all directions, nothing turning, nothing falling, nothing forming. The universe was not like that. It was close, extraordinarily close, but not exact. And the story of why rotation exists begins with what that difference was. Before we get to the large-scale origin of spin, though, there is another kind of spin entirely, and it is worth pausing on, because it complicates the picture in a way that turns out to matter. In 1922, the German physicists Otto Stern and Walther Gerlach conducted an experiment that was not designed to discover what it discovered. They fired a beam of silver atoms through a magnetic field that was deliberately uneven, stronger on one side than the other, expecting the beam to spread into a continuous band, as the physics of the day predicted it would. Instead, the beam split into two discrete components. Two, not a spread. Two distinct spots on the detector plate, with nothing in between. There is a detail in how they saw the result that is too good to leave out. The silver deposit on the detector was at first invisible, far too thin to see. Gerlach was examining the plate when he noticed the faint trace beginning to darken and resolve into two lines. The reason it developed at all, as Stern later told the story, was that he had been smoking the cheap, sulfur-rich cigars he could afford on a junior physicist's salary, and the sulfur in his breath reacted with the silver to form silver sulfide, which is black, and which made the pattern visible. A poorly paid physicist's bad cigars are, in a small and literal way, part of how the quantization of spin was first seen. The two spots were a problem. If the silver atoms had angular momentum only from the orbital motion of their electrons tracing paths around the nucleus, that angular momentum could, in principle, point in any direction. The uneven magnetic field should have deflected the atoms by every amount in between, producing a smear. Two clean spots meant something else was going on. Whatever angular momentum the field was responding to came in only two values, and nothing else was allowed. It took 3 years for the explanation to arrive. In 1925, two graduate students at Leiden University in the Netherlands, George Uhlenbeck and Samuel Goudsmit, proposed that the electron itself carries an intrinsic angular momentum, entirely independent of its orbital motion. They called it spin. The electron, in their picture, behaved as if it were a small sphere rotating on its axis, and that rotation produced a magnetic moment, which was what the magnetic field had been pushing on. The words, as if are doing a great deal of work in that sentence, because the electron cannot actually be a small sphere rotating on its axis. If it were, and if its angular momentum had the value the experiments demanded, then a point on its surface would have to be moving faster than light to keep up. This is not allowed. The conclusion is not that the electron spins impossibly fast. The conclusion is that the electron has no surface in that sense at all. It is not a tiny ball, and yet it has angular momentum. And yet that angular momentum comes in exactly two values, spin up and spin down, and nothing in between. Spin, in this sense, is not rotation. It is a purely quantum property, with no classical picture that is quite right. Physicists sometimes describe it with a sentence that is half joke and half confession. Spin is like a ball that is spinning, except it is not a ball and it is not spinning. What it actually is a form of intrinsic angular momentum, something the particle simply has, the way it has mass or electric charge, that cannot be switched off, transferred away, or altered by any ordinary process. The proposal was not welcomed at first. Ralph Kronig, a young physicist working at Columbia University, had arrived at the same idea electron spin as an intrinsic property some months earlier. He showed it to Wolfgang Pauli, one of the most formidable theorists of the era, and Pauli dismissed it. The required surface speed was obviously impossible. The idea was too crude. Kronig, discouraged, did not publish. Then Uhlenbeck and Gaudsmit reached the same conclusion independently, took it to their supervisor Paul Ehrenfest, and Ehrenfest did the thing Pauli had not. He told them to submit it. He also told them, by their own later account, that they were young enough not to have ruined their reputations if it turned out to be wrong, which, depending on how you read it, is either reassurance or a warning. The paper appeared in the autumn of 1925. Kronig is remembered as the man who got there first and was talked out of it. Pauli's skepticism is understandable, but Pauli had, that very same year, noticed something that needed exactly this kind of explanation. He had proposed his exclusion principle. No two electrons in an atom can occupy the same quantum state at the same time. To specify a quantum state, you needed a set of quantum numbers, and Pauli had found that 3 of them were not enough to account for the observed structure of atoms. There had to be a 4th. He called it, carefully, a two-valuedness, not describable classically. Spin was that 4th quantum number. With it, the exclusion principle became complete. Each electron in an atom is described by 4 quantum numbers, including its spin, which is either up or down, and no 2 electrons share all 4. The consequences of this are not abstract, and they are not far away from you. Without the exclusion principle, every electron in an atom would collapse into the lowest available energy level. There would be no shells, no distinct chemical elements behaving in distinct ways, no molecules, no variation across the periodic table. Everything made of atoms, the floor beneath you, the air above you, the body lying still in the dark, holds its shape because electrons are forbidden from sharing a quantum state. And that prohibition rests on spin. In 1940, Pauli, working with the Swiss physicist Marcus Fiers, proved what is now called the spin statistics theorem. When you combine quantum mechanics with Einstein's special relativity, a connection between a particle's spin and its statistical behavior follows as a mathematical necessity. Particles with half-integer spin like electrons obey the exclusion principle. Particles with whole integer spin do not. This was not an extra assumption bolted on to make the numbers work. It falls out of the mathematics on its own. Spin is required by the structure of relativistic quantum theory. Matter is stable because the theory leaves it no other option, and the divide it draws runs straight through the world. The 2 families it sorts particles into are not a technicality. They are the difference between the matter that takes up space and the forces that pass through it. The particles that build solid things, electrons, protons, neutrons, all of them half-integer in spin, are the ones forbidden to share a state. And that refusal is why matter is rigid, why your hand does not pass through the table, why atoms stack into structures instead of collapsing into a point. The other family, the whole integer particles, do the opposite. Far from being forbidden to share a state, they prefer to. Photons, the particles of light, are of this kind, and so are the carriers of the other fundamental forces. Pile enough of them into the same state, and they reinforce rather than resist, which is, at bottom, why a laser can exist at all, why countless particles of light can march in perfect step where countless electrons never could. Cool certain kinds of atoms close enough to absolute zero, and they too will collapse together into a single shared quantum state, a substance that behaves as one thing rather than many. Whether a particle hoards its state or shares, it comes down to a single number, the value of its spin. The strange two-valued property that split a beam of silver atoms turns out to be the dividing line between what can be built and what can be beamed. There is one more measurement worth placing here. because it shows how seriously this is meant. If you treat the electron as a tiny classical magnet, its magnetic strength should correspond to a certain number. The quantum theory of the electron predicts not that number but almost exactly twice it, and then, with the next layer of theory added, predicts small corrections to that doubling, digit after digit. The measured value of the electron's magnetic moment now agrees with the prediction to more than 10 decimal places. It is among the most precisely confirmed numbers in all of science. The strange, surfaceless, two-valued thing called spin is not a placeholder for ignorance. It is one of the best understood quantities we have. It is worth following this property one step further, because the exclusion principle that spin makes possible does something you can stand on. When Pauli forbade two electrons from sharing the same quantum state, he did more than organize the periodic table. He created a kind of resistance that has nothing to do with electric charge or with heat. Pack electrons closely enough together, squeeze them into a smaller and smaller volume, and they begin to push back, simply because there are no unoccupied states left for them to move into. They cannot be forced to share. This refusal generates a pressure, degeneracy pressure, it is called, and it does not weaken as the material cools. An ordinary gas loses its pressure as it loses heat. Degeneracy pressure does not. It is there because of the exclusion principle alone, and it would be there at a temperature of absolute zero. For most of the matter you encounter, this pressure is irrelevant. It only becomes important when gravity has nothing left to oppose it. Consider a star like the Sun, late in its life. It has burned through its hydrogen, swollen and shed its outer layers, and what remains is a core with no fuel left to burn. Without the outward push of fusion, nothing holds the core up against its own weight. It collapses, and it keeps collapsing until the electrons are crushed close enough together that degeneracy pressure halts the fall. What is left is a white dwarf, an object with roughly the mass of the Sun compressed into a sphere about the size of the Earth, held up not by heat, not by burning, but by the simple fact that its electrons cannot occupy the same states. A spoonful of it would weigh as much as a small car. It is held against gravity by a quantum rule, but there is a limit to what that rule can hold. In the early 1930s, a young physicist named Subrahmanyan Chandrasekhar worked out, on a long sea voyage from India to England, what happens when a white dwarf is too heavy. He found that above about 1 4/10 times the mass of the Sun, the electrons would have to move so fast to resist the crushing weight that they would approach the speed of light, and at that point degeneracy pressure can no longer keep up. Above that mass, the white dwarf cannot support itself. The result was not welcomed at first. One of the most eminent astronomers of the day dismissed it publicly and at length. But the limit was real, and it carries Chandrasekhar's name to this day. What happens to a stellar core that exceeds it? Gravity wins the next round. The electrons are driven into the protons, the two combining into neutrons, and the collapse resumes faster, deeper, more violent until the neutrons themselves become degenerate, and a new degeneracy pressure, this time among the neutrons, brings the fall to a stop. The object that remains is a neutron star, the mass of the Sun packed into a sphere the width of a city, held up by the same refusal to share quantum states, now operating among neutrons instead of electrons. The spin property that began as a puzzle in a beam of silver atoms turns out to be the thing standing between a dead star and total collapse. And it is the neutron star, born in exactly this way, that carries us to the most extreme demonstration of ordinary rotation in the entire universe. So here is where we are. There are two very different things called spin. There is quantum spin, the intrinsic angular momentum of fundamental particles, with no classical equivalent, required by relativistic quantum mechanics, responsible through the exclusion principle for the very existence of structured matter. And there is classical angular momentum, the rotation of objects, the spin of tops and skaters and planets and galaxies, conserved through ordinary processes, amplified by collapse. The two share a name and a mathematical form. They are not the same thing, and confusing them leads nowhere. The spin of the electron was not inherited from a rotating nebula. The spin of a galaxy was not handed down from the quantum state of its electrons. What connects them is subtler, and it runs not through analogy but through history. The quantum spin of the electron is a property fixed by the structure of the laws themselves. The classical rotation of galaxies traces back to faint irregularities in the early universe. Neither was chosen. Both were set by conditions that existed before anything we would recognize as structure had formed. The question is how those conditions produced the particular pattern of spin we actually see: planets turning around stars, stars wheeling around galactic centers, galaxies strung along filaments, all of it in motion. And that question cannot be answered by conservation alone. You have to go back further than the solar nebula. You have to go back to a time when there were no nebulae, no stars, no galaxies, only an almost perfectly smooth universe, and the faint quantum noise that kept it from being exactly so. That is where the rotation came from. But to see why it came from there, it helps first to look at the most extreme demonstration of conservation itself, the object that takes a modest spin, collapses it to an almost unthinkable scale, and turns faster than anything else we have ever measured. In 1982, a radio astronomer named Donald Backer was working through data from the Arecibo Observatory in Puerto Rico when he encountered a signal he could not at first account for. It was a pulsar, a rotating neutron star sweeping a beam of radio waves past the Earth once per rotation, so that we receive a regular pulse, like the flash of a lighthouse seen from a passing ship. Pulsars were not new. Jocelyn Bell had found the first one in 1967 as a graduate student at Cambridge, picking out a signal so precise and so regular that her group only half-jokingly labelled the source "little green men," because no natural object was then known to keep time that well. It is worth staying with Jocelyn Bell for a moment, because her part in this is easy to compress into a single sentence and lose. She was a research student, building the radio telescope she would use physically building it, hammering posts and stringing wire across several acres of field, and then analysing its output, which arrived as ink traces on long rolls of paper, more than 30 meters of chart for every day of observation. She was the one who noticed a small piece of what she later called scruff, a smudge in the trace that did not behave like interference, and did not behave like a known source. She found that it returned at the same point in the sky, on a precise schedule, and that the pulses within it were spaced with a regularity that nothing natural was then known to produce. She tracked it down by hand, by attention, through a quantity of data that would now be handed to a computer. The discovery was recognized with a Nobel Prize in Physics in 1974. The prize went to her thesis supervisor and to another senior astronomer. Bell, who had found the signal and established that it was real, was not included. The omission was noticed and debated at the time, and has been debated since. It became one of the most cited examples in the long argument about how credit is assigned in large scientific projects. Bell herself responded to it with a grace that has become almost as well known as the discovery, arguing that prizes should generally go to those who direct the research, and declining to express bitterness. Decades later, in 2018, she was awarded a major physics prize carrying a sum of money larger than the Nobel, and she gave the entire amount away, establishing a fund to support students from groups underrepresented in physics. The first pulsar she found is still there, still turning, still sending its pulse across the same stretch of sky. In the 15 years since, hundreds had been catalogued. Most pulsed once every few seconds, or a few times a second. This one was pulsing 641 times a second. Backer and his colleagues checked the data. They checked it again. The signal was real. The source was a neutron star spinning 641 times every second, and it had been doing so, as far as anyone could tell, for a very long time. It carried a catalogue designation that says nothing about how strange it is, a string of letters and numbers marking its position in the sky. For 24 years, it was the fastest spinning confirmed object in the universe. Then, in November 2004, a graduate student at McGill University in Montreal named Jason Hessels was working through observations from the Green Bank Telescope in West Virginia. He was searching a globular cluster called Terzan 5, a dense swarm of old stars roughly 18,000 light-years away, in the direction of the constellation Sagittarius. Globular clusters are good places to hunt for fast pulsars because the stars are packed so closely that they encounter one another often, and those encounters, as we will see, can wind a pulsar up. Hessels found what he was looking for, and rather more than he expected. The signal he picked out in November was confirmed in January of the following year. The pulsar it came from was rotating 716 times per second. not 641. 716. 716 full rotations every second, close to 43,000 turns in a minute. To picture what that means on the surface, you have to know how large the star is, and here there is genuine uncertainty, because the radius of a neutron star is known only to lie somewhere between about 10 and 16 kilometers. Take the upper end of that range, and a point on the equator of this object is moving at something near 70,000 kilometers per second. That is approaching a quarter of the speed of light, a surface moving at nearly a quarter of the speed of light. On an object the size of a city, with the mass of a star, the numbers do not get easier to hold the longer you look at them. Hessels presented the result to the American Astronomical Society in Washington. The pulsar sits in Terzan 5 to this day, turning 716 times a second, its equator tearing through space at a speed that makes every spinning thing in ordinary human experience engine parts. Centrifuge, the fastest industrial turbines ever built, seem, by comparison, almost geological in their slowness. This is conservation of angular momentum at its most compressed. A neutron star forms when the core of a massive star, having burned through its fuel, can no longer hold itself up against its own gravity and collapses inward. The collapse is fast in under a second. A core perhaps the size of the Earth falls to a sphere a dozen kilometers across. Angular momentum is conserved throughout. The original core was rotating slowly, by the standards of what it was about to become, but not at rest. As the radius drops by a factor of tens of thousands, the rotation rate climbs by the square of that factor to keep the total fixed. The slow turn of a dying stellar core, run through that collapse, comes out the other side as tens of rotations a second. It is the figure skater again, pulling her arms in, except the arms are an entire star, and they are pulled in over a distance of thousands of kilometers in less time than it takes to read this sentence. Newly formed pulsars typically spin somewhere between 10 and 100 times per second. That is already fast. 716 times a second is something else, and it does not get there by collapse alone. It gets there by a second process, and that process shows, more clearly than anything, how angular momentum passes from one object to another. The fastest known pulsar is what astronomers call a recycled pulsar, or a millisecond pulsar. It was not born spinning this fast. It began as an older, slower pulsar that happened to have a companion, another star, orbiting close. As that companion aged and swelled into a giant, it began shedding material from its outer layers. Some of that gas fell toward the neutron star, spiraling in through a flattened accretion disk flat. Again, for the same reason everything else is. The infalling gas carried angular momentum, drawn from the companion's orbit, and as it struck the neutron star and joined it, it handed that angular momentum over, grain by grain. Over millions of years, the old slow pulsar was wound back up, like a flywheel driven by a steady stream of incoming matter. The companion's orbital motion became the neutron star's spin. When the companion was finally exhausted, the recycling stopped, and what was left was a neutron star turning 716 times a second. The spin did not come from nowhere. It came from a dead star's orbit. Some of these systems end more violently than that, and the names astronomers have given them are unusually blunt. A black widow pulsar is a recycled pulsar whose spun-up radiation is now so intense that it is evaporating the very companion that fed it, boiling the smaller star away over time, like a spider consuming its mate. A redback does something similar to a slightly larger companion. These are not poetic exaggerations. They are catalogued classes of binary system, and in them you can watch the final stage of the exchange. The neutron star takes the orbit's angular momentum, takes the companion's mass, and then destroys what remains of the thing that gave it both. There is a ceiling to all this. Theoretical models suggest that a neutron star would tear itself apart at somewhere around 1,500 rotations per second. At that rate, the outward pull at the equator would overwhelm the almost unimaginable forces holding the star together, and it would shed its surface into space. No confirmed pulsar comes close to that limit. The fastest known sits at under half of it, which means there is room above, and we may yet find something faster. In 2007, A preliminary signal suggesting 1122 rotations per second was reported from another source, which would have broken the record by a wide margin. But the signal was only suggestive, not strong enough to count as a detection, and it was never confirmed. The record still stands where Hessel's left it. There is a reason astronomers care about these objects beyond the spectacle of their speed. A millisecond pulsar is one of the most precise natural clocks in existence. The beam sweeps past with such regularity that the arrival time of each pulse can be predicted years in advance, and the best of these pulsars keep time to a standard that rivals the atomic clocks on Earth. This precision turns them into instruments, because anything that subtly changes the distance between us and the pulsar, a passing ripple in spacetime, the slow tug of an unseen companion shows up as a tiny shift in when the pulses arrive. Astronomers use arrays of these pulsars scattered across the sky as a kind of galaxy-sized detector, watching for the long, slow gravitational waves expected from pairs of enormous black holes circling each other at the centers of distant galaxies. A clock that exists because a stellar core conserved its angular momentum during collapse becomes a way to feel the vibrations of the largest objects in the universe. But the clocks are not perfect, and their imperfections are themselves revealing. Every so often, a pulsar will abruptly speed up its rotation rate jumps by a tiny fraction in an instant, then slowly relaxes back. These events are called glitches, and they are thought to be windows into the interior of the star, where a superfluid core, rotating slightly faster than the rigid crust around it, periodically transfers some of its angular momentum outward in a sudden catch-up. There is also evidence, in some stars, of what are called starquakes. The crust of a neutron star is rigid and under almost unimaginable strain, and as the star slows over time and its shape adjusts, the crust can crack and settle, shifting the distribution of mass and, with it, the rate of spin. Even here, at the level of a fracturing crust on a city-sized star, the bookkeeping is the same. Move the mass inward, and the spin quickens. Let it settle outward, and the spin eases. The figure skater's arms, written in neutron degenerate matter. The millisecond pulsar is the single clearest example of what angular momentum conservation actually does when it is pushed to an extreme. A gas cloud spins slowly, it collapses, and spins faster. The resulting star, in a binary, pulls in its companion's orbit over millions of years and converts it to spin. And what comes out the far end is a city-sized object with the mass of the Sun, turning more than 700 times a second, its surface moving at a sizable fraction of the speed of light. Every step in that chain is the same law, written larger and smaller. What the millisecond pulsar does not explain, and what makes it, in the end, a demonstration rather than an origin, is why the first gas cloud was spinning at all. Conservation carried the spin through the collapse, and amplified it through the accretion. But the spin was already there to begin with. The law tells you what happened to it. It does not tell you where it came from. The solar system tells the same story, but with a complication that took 2 centuries to resolve. The solar system is a disk flat, ordered, with all the planets orbiting in the same direction, most of them turning the same way, all of them lying in nearly the same plane, as if someone had drawn them out on a single sheet of paper. The disk shape follows directly from conservation during collapse, exactly as we have already seen. Material falls freely along the spin axis, but is held out to the sides, so everything settles into a plane. That part is straightforward. What is not straightforward is what you find when you actually measure where the spin went, because the numbers do not behave the way the first theories predicted, and the gap between the prediction and the measurement nearly killed the correct explanation for 200 years. Immanuel Kant was 41 years old in 1755 when he published a book with the long title Universal Natural History and Theory of the Heavens. He was not yet the philosopher he would become that came later, with the Critique of Pure Reason in 1781. In 1755 he was working on cosmology, and what he proposed was this: a slowly rotating cloud of gas and dust, drawn together by its own gravity, would collapse and flatten into a spinning disk. From that disk, a star would form at the center, and planets would condense at various distances out. The planets would orbit in the same direction as the original rotation. The whole arrangement would be flat, because it had formed from something flat. This was correct. Not approximately correct, correct in its essential structure, the same picture that modern theory uses. Kant reached it through reasoning rather than observation. With the instruments and data of the mid-18th century, and what he produced was one of the most accurate, large-scale models in the history of astronomy. Pierre-Simon Laplace arrived at the same picture independently, in 1796. His version was more quantitative than Kant's. He proposed that as the cloud cooled and shrank, conservation of angular momentum would force it to spin faster, and that the rising speed would throw off rings of material at intervals. Those rings would later gather into planets, and the Sun would form from what stayed at the center. The combined idea became known as the nebula hypothesis, and it dominated thinking about the solar system for about a century. It explained the orbits, the disk, the shared direction of motion, the general layout. It was the right framework. Then the measurements came in. The Sun contains 99.87% of all the mass in the solar system. Everything else, all 8 planets, every moon, every asteroid, every comet, every grain of rock and ice and gas that circles the Sun, adds up to the remaining 0.13%. If you think only in terms of mass, the solar system is essentially the Sun, with a rounding error scattered around it. Now measure the angular momentum, the spin budget, rather than the mass budget. The Sun, turning slowly on its axis, holds less than 0.5% of the solar system's total angular momentum. Jupiter alone, one planet, far out, with about 1,000th of the Sun's mass, carries more than 60% of it. The 4 giant planets together hold well over 90%. The body with almost all the mass contributes almost nothing to the rotation. The bodies with almost none of the mass carry nearly all of it. These two facts, placed next to each other, do not resolve themselves quickly. The object with 99.87% of the mass has less than 0.5% of the spin. If the solar system formed from a single rotating cloud, as Kant and Laplace said, the Sun should have inherited the lion's share of the angular momentum along with the lion's share of the mass. It did not. Something stripped the spin out of the forming Sun, or moved it outward, before or during the building of the planets, and whatever that process was, it pushed an enormous fraction of the system's rotation into the outer orbits and left the center turning lazily. This was noticed in the late 19th century, and it was treated as a serious problem. James Clerk Maxwell, better known for the equations of electromagnetism, had already shown, studying Saturn's rings, that a smooth ring of orbiting material at different speeds will not simply condense into a single body the way Laplace had imagined. The shearing tears it apart. Combined with the spin budget that made no sense, the nebula hypothesis began to look untenable. By the early 20th century, many astronomers had set it aside. What replaced it, for a time, was a far more dramatic idea. The British physicist James Jeans argued, around 1917, that the planets had not formed from any cloud at all. They had been torn out of the Sunday. In this picture, another star had passed close to the Sun long ago, and the gravitational pull of that near miss had drawn a long filament of hot solar material out into space, and that filament, cooling and breaking up, had become the planets. It was a tidal theory, a collision theory, and it had one great attraction. It sidestepped the spin problem entirely. If the planets were dragged out of the Sun by an external encounter, the strange distribution of angular momentum looked less mysterious. The theory was vivid, and it held the field for decades. It was also wrong, and establishing that took a long time. The problems accumulated slowly. First, close stellar encounters are extraordinarily rare. The typical distance between stars in our part of the galaxy is several light years, and 2 stars passing near enough to pull planetary filaments out of each other almost never happens. If planets required such an event, the galaxy should contain almost none. We now know planetary systems are common. Thousands have been found around other stars, and something common cannot depend on something almost impossible. Second, the material drawn from the Sun would be searingly hot, the exposed interior of a star. Hot gas expands and disperses. It does not cool quietly into worlds. The filaments Jeans imagined would have blown apart into thin interstellar gas long before they could gather into planets. Third, the fine architecture of the solar system, the tilts of the planets, the arrangement of their moons, the structure of the asteroid belt points to a long, gradual process of building up from small bodies, not a single catastrophe. So the tidal theory was set aside, and the nebula hypothesis was revived. But the spin problem it had been invented to escape was still there, waiting. If the solar system formed from a rotating cloud, and angular momentum is conserved, the sun should be spinning far faster than it is. The cloud that made it carried, by any reasonable estimate, far more rotation in its sun-forming material than the sun now contains. Where did that rotation go? The answer needed 20th century physics, and it turns on the magnetic field of the young Sunday. A newborn star is not the quiet object the sun is today. It spins rapidly, and it carries a magnetic field far stronger than the sun's present one. That field threaded out into the surrounding disk of gas, and because the gas was ionized, electrically charged, and therefore gripped by magnetic field lines, the field effectively tied the spinning star to the spinning disk, like elastic threads running from the center out into the surrounding material. Through that magnetic linkage, angular momentum was dragged outward out of the sun, into the disk, and from the inner disk to the outer disk, and finally into the orbits of the forming planets. The sun was braked by its own field acting on its own disk. Its spin bled away. The disk absorbed it and carried it outward into the planetary orbits. Jupiter and Saturn formed far out, where it was cold enough for ice and gas to pile up into enormous bodies. Being both massive and distance matters here, because angular momentum grows with the square of the distance from the axis. They caught the largest share of the outward flowing spin. More than 60% of it ended up carried by Jupiter's orbit alone. The Sun was left with a few tenths of a percent, turning once about every 25 days, which is slower than several of its own planets orbit it. This process is called magnetic braking, and it is not a story told only about the Sunday. We can watch it happening elsewhere. Young stars across the galaxy, the ones still wrapped in their birth disks, a class often called T Tauri stars, after the first of the type to be recognized, tend to spin more slowly than you would expect from collapse alone, and the ones that have lost their disks tend to spin faster, having been released from the brake. The disk and the slow rotation go together. For most of the history of this idea, the disk Kant imagined was something inferred rather than seen. No one had ever looked at a young star and watched a flat, rotating sheet of gas and dust circling it, waiting to become planets. The picture was correct, but it was a deduction. That changed within living memory. When observatories capable of seeing in the longer wavelengths the heat glow of cold dust, rather than visible light, were turned on nearby star-forming regions, the disks were simply there. In the Great Nebula in Orion, a nursery of newborn stars about 1,300 light-years away, telescopes found dozens of young stars, each wrapped in a dark, flattened disk, silhouetted against the bright gas behind them. They had a name almost at once: propleds, short for protoplanetary disks. Kant's flat rotating sheet, sketched from reasoning in 1755, photographed at the end of the 20th century. The most striking confirmation came in 2014, from an array of radio dishes high in the Chilean desert, working together as a single instrument. They pointed at a young star known as a T Tauri star, only about 1 million years old, and produced an image of its surrounding disk in extraordinary detail. The disk was not featureless. It was carved into a series of bright rings separated by dark gaps, and the most natural reading of those gaps is that planets, already forming within the disk, had swept their orbits clear of material. Here was a system in the act of doing exactly what the nebula hypothesis described: a flat, rotating disk, born from a collapsing cloud, organizing itself into the spacing of a planetary system, the rotation and the disk and the planets all in one frame. The process by which the dust in such a disk becomes planets has its own history of being worked out. Early in the 20th century, around the time the tidal theory was briefly in favor, 2 researchers in Chicago proposed that planets had grown by the slow accumulation of small solid bodies. They coined the term planetesimal for these building blocks, the seeds from which worlds assemble. The idea was that fine dust in the disk sticks together into grains, grains into pebbles, pebbles into boulders, boulders into bodies kilometers across, and these planetesimals then collide and merge, the larger ones gravitationally sweeping up the smaller until a handful of survivors have cleared their orbits and become planets. This is, in its essentials, the modern picture. The disk spins, the dust within it settles and clumps, and the planets that emerge inherit the rotation of the disk they grew from, which is why they orbit in a plane and in a single direction. The slow rotation of the star and the orbital motion of its planets are two halves of one inheritance. The detailed mechanics, exactly how the angular momentum threads through the disk, how the field couples and slips, are still being worked out, and the models do not all agree in their fine structure. But the broad picture is solid, and it is visible in the sky in stars being born right now. What this means for Kant and Laplace is that they were right in the ways it was possible to be right with the knowledge they had, and wrong in a way that only later physics could repair. The cloud collapsed, the disk formed, the planets condensed from it. The one thing they could not have known was that the sun's spin would be carried off by magnetic coupling to its own disk, that the very problem their theory created would be solved by a force whose laws had not yet been written when they wrote. The tidal theory was a 100-year detour. Jeans was wrong. Kant was right. The current account of how the solar system formed, the one that survived the spin problem, the discovery of planets around other stars, the samples returned from asteroids, the close surveys of disks around newborn stars, is essentially the one Kant sketched in 1755, with magnetic braking added and a great deal of detailed work filled in. A rotating cloud collapsed. A disk formed. Angular momentum moved outward through magnetic coupling. The inner disk made rocky worlds. The cold outer disk made ice and gas giants. The giants took most of the spin. The sun was left turning slowly. None of it was arranged. It happened because angular momentum is conserved, because magnetic fields grip ionized gas, because gravity pulls harder on what is closer, because the square of the distance matters. The shape of the solar system is simply the record of those rules running their course over a few million years. But notice what this still does not address. The cloud that became the solar system was already turning, faintly, before the collapse began. Magnetic braking redistributed that rotation. It did not create it. The disk formed because spin was present, and the collapse amplified it. So the question only moves one step back and grows larger. Where did the rotation in that cloud come from? It is not a question about the solar system alone. Every gas cloud that has ever collapsed into stars carried some net rotation. Every galaxy turns. The galaxy you are inside right now, the Milky Way, is turning, carrying the solar system around its center at 828,000 kilometers per hour, one full circuit every 225 to 250 million years. That rotation was not produced by any accretion disk or magnetic brake. It was there before the galaxy was a galaxy. To find where it came from, you have to go back before there were any clouds at all. The solar system's cloud was turning before it collapsed. That much we have established. What the story so far cannot answer, working from the solar system alone, is how the turning got into the cloud in the first place. The cloud did not form in isolation. It sat inside a galaxy, among other clouds, inside the gravitational field of everything around it. And it is precisely that surrounding gravity, slightly stronger on one side than the other, slightly off-center, that set the cloud turning. Before following where that turning came from, it is worth being sure of the fact itself that galaxies rotate, because the way we came to measure it carries a surprise that bears directly on the rest of this story. That galaxy's turn was suspected long before it was confirmed. A spiral galaxy looks like something caught mid-rotation, its arms trailing as though wound up by a spin. But suspicion is not measurement. The confirmation came from light. A galaxy turning broadside to us has one edge rotating toward us and the other rotating away, and that motion stretches the light from the receding edge toward longer, redder wavelengths and squeezes the light from the approaching edge towards shorter, bluer ones. Measure that shift across the face of a galaxy, and you can read off how fast each part of it is turning. The astronomer who did this most carefully, through the 1960s and 70s, was Vera Rubin. Working often through the night at telescopes where she was, for years, one of very few women admitted to observe at all, she measured the rotation of spiral galaxies edge by edge, plotting how orbital speed changed with distance from the center. She expected what everyone expected, that the stars far out at the edge, where the visible matter thins to almost nothing, would orbit slowly the way the outer planets of the solar system orbit slowly, because there was little mass out there to hold them and little gravity to require speed. That is not what she found. The outer stars were moving just as fast as the inner ones. The rotation curve, instead of falling off toward the edge, stayed stubbornly flat, mile after mile out into the dark. There was only one way to read it. For the outer stars to orbit that fast without flying off into space, there had to be far more mass present than anyone could see, a great unseen reservoir of matter, extending well beyond the glowing disk, gripping the galaxy with its gravity. Rubin's flat rotation curves became one of the most direct pieces of evidence for what is now called dark matter, the invisible substance that, on current understanding, outweighs all the visible stars and gas by a wide margin and forms vast halos around every galaxy. She had set out to measure how galaxies turn, and had instead measured the shadow of something nobody had seen. This matters for what follows, because it is those dark matter halos, not the bright disks of stars, but the great invisible structures around them that tidal torque theory is really about. When the theory predicts the spin of a galaxy, it predicts the spin of the halo. The visible galaxy is a bright deposit at the center of a far larger turning thing, and it is the turning of that larger thing, set going in the early universe, that the next part of the story has to explain. Rubin established that the halos are there, and that they rotate. The question is what started them. This is tidal torque theory, and its history is a quiet lesson in how an idea can travel. It arrived once and went unheard, arrived again 2 decades later in a slightly different form, and only reached its finished shape through work spread across more than 30 years and several countries. The first person to propose it was Fred Hoyle. Hoyle is remembered for other things for coining the term Big Bang, which he meant dismissively in a radio broadcast in 1949, for his work on how the elements are forged inside stars, for a string of later, increasingly unorthodox positions that put him at odds with most of his field. He was a physicist of real originality and real stubbornness, a Yorkshireman who trusted his own judgment past the point where most people would have stopped. In the same year as that broadcast, at a conference, in the middle of a discussion about how galaxies form, he suggested that galaxies might have got their rotation from the tidal pull of their neighbors, that the matter destined to become a galaxy would be twisted by the gravity of the matter around it, and from that twisting would acquire a net spin. The idea landed quietly. It was not published in any major form. It drifted through the literature as a footnote to his other work, and the discussion moved on. 20 years passed. In 1969, the Princeton physicist Jim Peebles, already laying down some of the foundations of modern cosmology, arrived at the same idea independently and carried it much further. He had not gone looking for Hoyle's proposal. He worked through the problem of how rotating disks of galaxies could form in an expanding universe, modeled the gravitational pull between neighboring clumps of forming matter, and showed that the tidal twisting from those neighbors would naturally hand angular momentum to a collapsing structure. His calculation predicted a typical amount of spin for a galaxy's halo, expressed as a single dimensionless number, a measure of how much of the structure's motion is orderly rotation rather than random milling about of roughly 8/100ths. Later observations and computer simulations would find real galaxies clustered around that range. Peebles had looked into the gravitational arithmetic of the early universe and found the origin of galactic spin sitting inside it. A year later, in 1970, the Soviet cosmologist Yakov Doroshkevich extended the mathematics, showing how the angular momentum of a not quite spherical patch of forming matter grows in proportion to time during the early, gentle phase, the period when the lumps in the matter are still small enough to be treated with relatively simple equations. The shape mattered. A perfectly spherical patch would feel no net twist because the pull would be symmetrical. A lopsided one, and real patches are always lopsided, feels a torque, and the torque builds. The finished formulation came from the astrophysicist Simon White in 1984, in a paper that drew the earlier work together into what is now called tidal torque theory. White made the mechanism precise. A forming halo of matter gains spin during that early phase because of a misalignment. Its own shape, the way its mass happens to be distributed, is not lined up with the external gravitational field pulling on it from the surrounding structures. Because the patch is not spherical, and because the field is not uniform, the two are tilted relative to each other, and that tilt produces a steady twist. the angular momentum accumulates. It does not accumulate forever. There comes a moment cosmologists call turnaround, the point at which a region has expanded as far as it will, stops being carried outward by the general expansion of the universe, and begins to fall back in on itself under its own gravity. Around turnaround, the tidal twisting loses its grip. Whatever spin has built up by then is essentially locked in, and the collapse that follows simply conserves it, amplifying it the way every collapse does. The galaxy that emerges carries the rotation the tides gave it, frozen at the moment it began to fall. Hoyle in 1949, Peebles in 1969, Doroshkevich in 1970, White in 1984. 35 years from first suggestion to settled framework, with the man who first suggested it largely passed over by the history. The framework gets the typical amount of spin right it matches, in a broad statistical sense, the rotation of dark matter halos measured in computer simulations. It is less reliable about the direction of any single halo's spin. It predicts the right average strength, but the predicted orientation of a given galaxy's spin axis is only accurate to within something like 50 degrees when checked against simulations. The violent, nonlinear physics of the actual collapse scrambles some of the information the gentle early phase had written down. So it is a theory of the origin and the typical size of galactic rotation, not a precise forecast for any one galaxy. What it does, and does well, is tie the spin of every galaxy in the observable universe back to a single source. The confidence in this picture rests heavily on a kind of experiment that cannot be done in a laboratory. You cannot build a galaxy and watch it spin up. The process takes billions of years and structures larger than anything human, but you can build a universe inside a computer. Beginning in the 1970s, and growing steadily more ambitious as machines improved, cosmologists have run what are called many-body simulations. They fill a simulated volume with millions or billions of particles representing matter, set the initial conditions to match the tiny density variations seen in the oldest light, switch on gravity, and let the model run forward through cosmic time. Out of that smooth, almost featureless start, the simulated matter draws itself into a web sheets and filaments and clusters that looks remarkably like the real distribution of galaxies mapped by our telescopes. One of the most influential of these, run in the mid-2000s and tracking more than 10 billion simulated particles, was used to test exactly the prediction tidal torque theory makes. When the researchers measured the spin of the dark matter halos that formed in the simulation, the amount of rotation each acquired, expressed as that dimensionless spin parameter, the values clustered right around the figure the theory had forecast decades earlier, near 8/100ths. The halos had been torqued into rotation by their neighbors during the gentle early phase, exactly as predicted, and the distribution of their spins matched the calculation. The theory was not merely plausible, it produced a number, and the simulated universe returned that number. What this pushes the question back to is the character of those initial density variations, and that is where the chain reaches its deepest accessible link. The variations were not placed in the early universe by anything we can point to within the universe. The leading account is inflation, a brief interval in the first fraction of a second, when space expanded by an enormous factor, stretching microscopic quantum fluctuations, the irreducible jitter that quantum mechanics says even empty space must have up to the scale of the cosmos. Those stretched fluctuations became the density variations. The density variations seeded the tidal torques. The tidal torques became the spin of every halo, every galaxy, every filament. The rotation you can measure in the most distant structures in the sky is quantum uncertainty, frozen and magnified beyond all recognition, and then set turning by gravity over the age of the universe. That source is worth slowing down for, because it is the deepest point in the chain, and the rest of tonight hangs from it. Lie still for a moment, and imagine the universe a few 100,000 years after it began. There are no stars. There are no galaxies. There is only a vast, hot, nearly uniform haze of matter and light, filling all of space, glowing, the same in almost every direction you could look. Almost, not quite. Run a hand across that haze, and you would feel, here and there, the faintest unevenness, regions a hair denser than their surroundings, regions a hair thinner by about 1 part in 100,000. Nothing dramatic. A whisper of texture on something that is otherwise perfectly smooth. Everything that has ever formed every star, every galaxy, every planet, every turning thing, you included, grew out of that whisper. We can see it. The faint afterglow of that hot early universe still fills the sky, the oldest light there is, released about 380,000 years after the beginning, when the universe finally cooled enough to become transparent and let its light fly free. We call it the cosmic microwave background, and when we map it across the whole sky, it looks almost exactly the same in every direction, but the temperature wavers, place to place, by about 1 part in 100,000. Those wavers are the whisper of texture, frozen into light. They are the seeds. Here is how the chain runs. Those tiny differences in density were the lumps. The lumps pulled on one another with gravity. Where the matter was uneven and lopsided, the pull was off-center, and the off-center pull was a torque. The torque set the proto-galaxies turning. The turning was locked in at turnaround and amplified by collapse. And so the spin of the Milky Way, the spin that is carrying you around the galactic center at 828,000 kilometers per hour, as you lie here, traces directly back to the pattern of faint lumps in the early universe. There is no break in the line, a density difference of 1 part in 100,000, in a haze of matter nearly 14 billion years ago, became a torque, became a rotation that has not stopped since, and the lumps themselves go back further still. The current understanding is that they were sown during a fantastically brief, the fantastically rapid expansion in the universe's first instant, a phase called inflation which stretched the universe by an enormous factor in a tiny fraction of a second. Inflation took quantum fluctuations, genuine quantum noise, the same kind of intrinsic quantum unevenness that lies behind the spin of the electron and the split silver beam of Stern and Gerlach, and blew them up from subatomic size to the size of the cosmos. The quantum noise became the density lumps. The density lumps became the torques. The torques became the galaxy's spin. It is the same line, drawn from the smallest scale there is to the largest structures that exist. There was an early arrival picture, and it is worth knowing why it failed, because the reason is elegant. Before Hoyle, some physicists, the German Carl Friedrich von Weizsäcker in the 1940s, George Gamow, soon after proposed that the early universe was simply turbulent, full of swirling eddies from the start, and that galaxies inherited their spin from that primordial churning. It had a homely appeal. The universe was choppy fluid spin, galaxies formed in the chop. The trouble is that the kind of flow gravity produces as it pulls matter together has no curl to it, no built-in swirl. The early density ripples were, in the language of the field, irrotational. The motion they drove was straight infall, not circulation. A flow with no swirl in it cannot generate swirl on its own. To get rotation out of it, you need something from outside to break the symmetry, and that something is exactly the off-center tidal pull of the neighbors that Hoyle and Peebles had identified. The turbulence picture was set aside as the tidal account gathered support from simulations and from the sky, which leaves a question the section has been circling. Does tidal torquing work only at the scale of single galaxies and their halos, or does it reach further out onto the immense filaments of matter that string the galaxies together, the scaffolding of the universe itself? If the same off-center pull that spun up the Milky Way also acted on structures hundreds of millions of light-years long, then the rotation of the universe has a deeper architecture than a scatter of small, unrelated spins. That question has lately been given an answer from the sky. The filaments are turning. But before we follow the spin out to the largest scales it reaches, there are two worlds much closer to home that break the rule the tides laid down, and what happened to them shows what the clean story leaves out. Conservation of angular momentum explains why the solar system is a flat disk with everything orbiting the same way. Tidal torquing explains how the cloud got its spin to begin with. Between them, the two mechanisms account for the broad pattern of rotation at planetary and galactic scales. The planets go round the sun counterclockwise, as seen from above the sun's north pole, because the original cloud turned counterclockwise, and the collapse kept that direction. Most of the planets also spin counterclockwise on their own axes, because the disk they grew out of turned counterclockwise, and the material they swept up carried that turn into them. Most of them. Jupiter is tilted by 3 degrees. It spins very nearly upright relative to its orbit, exactly as you would expect from a planet that formed cleanly from a turning disk and was never badly disturbed afterward. Saturn is tilted by about 27 degrees, Earth by 23.5, Mars by 25. These tilts are not zero, but they are modest, and they fit a history of some collisions and gravitational nudging without anything catastrophic. Then there is Uranus. Uranus is tilted by 98 degrees. It does not spin upright. It does not even spin on its side in a way you could call ordinary. It rolls. Its axis lies almost flat in the plane of its orbit, so that one pole points nearly straight at the Sun at one point in its long year, and nearly straight away half an orbit later. Lie with that for a moment, because the consequence is genuinely disorienting. Picture standing near the North Pole of Uranus. The Sun climbs into the sky and then it does not set. It circles, low, and stays. For roughly 21 years, the length of a quarter of the planet's circuit around the Sun, that pole is held in continuous daylight, while the opposite pole sits in continuous dark. Then, slowly, over the following decades, the Sun sinks and the long day gives way to a night of equal length. A single season on Uranus lasts about 21 Earth years. There is nowhere on Earth, not even at our own poles, where the rhythm of light and dark runs that slowly. The planet has the most extreme seasons in the solar system, and they are measured not in months but in decades. Because the tilt is just past 90 degrees, Uranus counts, technically, as spinning backward relative to its orbit. But the truer description is simply that it was knocked over. The spin axis that should point roughly up and down, like every other planet's, instead points almost straight out to the side. The leading explanation is a giant impact. Sometime during the formation of the solar system, while the outer planets were still gathering their mass from the surrounding disk, Uranus was struck by something large, a body with perhaps half to a full Earth's worth of mass, one of the many protoplanets wandering the outer system in those first chaotic millions of years. The blow tipped the planet over. For a long time, a single such impact was the standard account, and it remains the most widely held. But in 2011, Alessandro Morbidelli, at the Côte d'Azur Observatory, and his colleagues published simulations suggesting that one impact has trouble with a particular detail: the moons. Uranus has 27 known moons, and most of them orbit in the plane of the planet's tilted equator, which means they share its 98-degree tilt. If a single great blow had knocked an upright Uranus onto its side after its moons had already formed, those moons should have been left behind in their original, upright orbital plane, not carried round to match the new one. For the moons to lie in the equatorial plane, either they formed after the tilting blow, from debris thrown out by it, or the tilting happened in more than one stage, with time for the moon system to settle into each new orientation. Morbidelli's team found that two impacts, each from a body of around half an Earth mass, fit the observed moon system better than one larger blow. The remark Morbidelli offered about it was careful but pointed. If Uranus was struck at least twice, then large impacts in the outer solar system were not exceptional events. They were ordinary. The tidy image of planets accreting peacefully from a calm disk had to make room for a reality in which the outer system, for its first tens of millions of years, was a place of repeated heavy collisions. Conservation still governs the whole thing, but conservation operates inside a system, and the system included worlds slamming into one another. Venus is the other exception, and it breaks the rule in a different way. Venus turns backward opposite to its orbit, and opposite to the Sun's own rotation. That alone would be notable. But Venus also turns astonishingly slowly. It takes about 243 Earth days to complete one rotation. Its year one trip around the Sun is about 225 Earth days. So a single day on Venus, measured from one sunrise to the next, is longer than its entire year. And because the spin is backward, the Sun, were you somehow able to watch it through that crushing atmosphere, would rise in the west and set in the east, creeping across the sky over the course of months. You could not, of course, watch it. The surface pressure is about 90 times the Earth's. The temperature is hot enough to melt lead, and the sky is permanently sealed under cloud. That cloud is also why no one knew how Venus rotated until quite recently. For centuries, astronomers tried to read the planet's spin from the drift of features in its cloud tops, and got answers ranging from hours to weeks, because the clouds move on their own, driven by ferocious winds and have little to do with the solid body beneath. It was only in the early 1960s, when radar from the new generation of radio telescopes could punch through the cloud, bounce off the rock below, and read the surface directly, that the truth came out. The body of Venus turns once every 243 days, and it turns the wrong way. Two explanations compete to account for it. The first is a giant impact, like the one that tipped Uranus a blow large enough to stop and reverse the planet's original spin. A study published in 2025 in the journal Astronomy and Astrophysics modeled a wide range of such collisions and found that many of them could reproduce Venus's present backward, sluggish rotation, head, on impacts onto a slowly turning Venus, and glancing strikes by Mars-sized bodies onto a faster turning one. Both led to the right end state. The study noted a telling side effect. The kinds of impact that reproduce Venus's spin leave very little material in orbit afterward, and that fits the fact that Venus, alone among the inner planets, except Mercury, has no moon. A spin-reversing blow of the right sort does not throw off a lasting ring of debris the way the impact that made our own moon is thought to have done. There is a small historical footnote here. For a couple of centuries, some observers believed Venus did have a moon, even gave it a name, Neith, but it was never real, only a trick of light in early telescopes, and Venus has been moonless all along. The second explanation needs no catastrophe, only time. The sun raises tides on Venus, not ocean tides, since there are no oceans, but tides in the solid rock, and more importantly, in the thick atmosphere. That heavy atmosphere, heated unevenly as the sun moves over it, develops vast standing patterns of pressure, and those patterns press on the planet below and exert a slow torque. Over billions of years, the combined drag of solar tides and atmospheric pressure could have slowed Venus's original forward spin, brought it to a near halt, and gradually walked it over into a slow backward turn. No impact required, just the patient grinding of the sun and the air. The honest answer is that we do not know which is right, or whether both played a part, with an impact setting up something near the present state and atmospheric drag, fine-tuning it across the ages that followed. The detailed spin history of Venus is still unsettled. Two missions now in preparation, the European one named Envision and the American one named Veritas, are meant to study the surface and interior closely enough to help decide between the stories. Neither has launched yet. What Venus and Uranus together show is the thing the clean tidal torque account leaves out. Tidal torquing hands a structure its starting spin during the gentle early phase, before collapse. But between that moment and now lie billions of years. And in those years, individual events of great impact, a gravitational resonance, a close encounter, can rewrite the spin of any single body. The rule is conservation, but conservation works inside a system, and the system has collisions in it. The Earth itself carries the clearest evidence that the system has collisions in it, and the consequences of one in particular hang in the sky every night. The leading explanation for the moon is a giant impact of its own, but one that went differently from the blows that tipped Uranus and reversed Venus. Early in the solar system's history, perhaps a few tens of millions of years after the planets began to form, a body roughly the size of Mars is thought to have struck the young Earth. The impactor has been given a name, Theia. The collision was enormous, energetic enough to melt much of the Earth and to throw a great quantity of vaporized and molten rock into orbit. And here is the contrast that matters. The debris from that impact did not disperse and did not fall back entirely. It settled into a disk around the wounded Earth, and that disk, rotating, collapsing, conserving its angular momentum exactly as a disk must, drew itself together into the moon. The same process that builds planets around a star, run in miniature around a planet, in the aftermath of a collision. This is why the Earth-Moon system carries so much of its angular momentum in the Moon's orbit, and why the Earth spins on a modest tilt rather than lying on its side. The impact that made the Moon set the present rhythm of the system, the length of the day, the existence of tides, the slow outward drift we will come to shortly. Venus was struck in a way that left it slow and turned around with no satellite to show for it. Uranus was knocked onto its side. The Earth was struck in a way that gave it a moon. The difference between these outcomes is the difference between the angle, the speed, and the size of what arrived the same physics, sorting three planets into three entirely different fates. The early solar system was, for its first several hundred million years, a place where such arrivals were ordinary rather than rare. The cratered face of the moon is a direct record of it, a surface old enough to have preserved the scars, marked by a long era of heavy bombardment when leftover debris from planet formation was still raining down across the inner system. The Earth bears the same history, though its scars have been erased by water and weather and the slow turning over of its crust. And the innermost planet, Mercury, carries the record in its rotation. Mercury does not spin freely. It is caught in a resonance with the Sun, turning exactly 3 times on its axis for every 2 orbits it completes. The Sun's gravity, acting over billions of years on a small, close planet, has locked its spin into a simple ratio, with its year another reminder that the rotation a planet is born with is only a starting value, and that the long pull of gravity and the chance of collision will edit it for as long as the system lasts. The spin Venus took from the forming disk was later altered, perhaps drastically, by something. The spin Uranus took was almost certainly knocked sideways, probably more than once. That is why the tilts are scattered, why a couple of planets turn the wrong way, why some moons orbit backward or at steep angles to their planet's equator. The solar system's present inventory of spin is not simply the original cloud's rotation handed tidally down through every scale. It is that original rotation, plus the record of 4.5 billion years of subsequent violence written over the top of it. In some places, the first signal still shows clearly Jupiter's small tilt, the orderly counterclockwise orbits. In others, it is mostly buried under what came later. At large enough scales, that buriedness reverses. No single collision can rearrange a galaxy cluster. No impact moves a filament of the cosmic web. The spin of structures that big is far closer to the original signal the tides wrote into the early universe, much less scrambled by later events, much more directly readable as a record of those first faint lumps. Which is exactly why it matters that the largest structures in the universe have now been caught turning, and why. To see what that turning is connected to, we have to come back, briefly, to a damp basement in Paris and a wire hung from a ceiling. In 1851, a physicist in Paris noticed something in the swing of a pendulum hanging from his basement ceiling that told him, more directly than any view of the stars had ever managed, that the ground beneath him was turning. He moved that observation onto a wire 67 meters long, hung it from the dome of the Pantheon, and invited people to come and watch the Earth move. His basement was damp and not large. Paris in January of 1851 was cold. Léon Foucault had strung a wire about 2 meters long from a support in the ceiling and fixed a small weight at the end, a pendulum, nothing dramatic. He set it swinging. Then he watched. The pendulum swung back and forth. That was expected. But the plane it swung in the flat, invisible sheet that the wire and the weight traced out between them was slowly, almost imperceptibly, turning. It was drifting clockwise, by a tiny fraction of a degree with each pass. Within a few minutes the drift was unmistakable. Within an hour it had turned far enough to be certain of. Foucault understood at once what he was seeing. The pendulum was not turning. A pendulum, once set going, holds its plane of swing fixed in space. It keeps swinging in the same direction relative to the distant stars, because nothing is there to turn it. What was turning was the floor beneath it. The Earth was rotating, and the pendulum, indifferent to that rotation, kept swinging in its fixed direction while the room revolved slowly around it. The drift he was watching was not the pendulum moving. It was the planet. He had begun in medical school years before, and left it on discovering that the fine, patient work of his hands suited instruments far better than it suited patients. He had done real work in photography, in optics, in measuring the speed of light. He was an experimenter of genuine gift, a man for whom a physical demonstration was as natural a way of speaking as an equation is for others. And what he had in that cold basement was something no one had achieved before, a direct, mechanical, visible proof that the Earth turns, not inferred from the motion of the stars, not deduced on paper, visible, in a room, to anyone standing there. He sent a short note to François Arago, then director of the Paris Observatory, and Arago arranged for a larger version of the experiment at the observatory itself, a pendulum, 11 meters long, swinging in the Meridian Room. Foucault presented the results to the Academy of Sciences in early February of 1851. Then he sent the invitation. It went to the scientists of Paris. A brief note. formal in its wording, plain in its meaning. The phrase from it has been quoted many times since. You are invited to come and see the Earth turn, not invited to observe an experiment demonstrating the rotation of the Earth, not invited to view a mechanical proof of the heliocentric system, invited to come and see the Earth turn as though the Earth were doing something you could simply go and watch, the way you might watch weather rolling in from the west. A few weeks after the Academy presentation, the larger version was ready. Foucault had secured the use of the Pantheon, the great domed building on the left bank, where France lays its honoured dead, its dome rising some 43 metres above the floor. From that dome he hung a wire 67 metres long. At the end of it swung a weight of 28 kilograms lead, coated in brass, compact and heavy, chosen to resist being pushed around by stray drafts. A fine point projected from the bottom of it. Below the weight, on the floor, lay a low ring of sand, and the point just cleared it. The first public demonstration drew dignitaries, among them the head of state. The weight was drawn carefully to one side and released with no sideways push at all, a clean release, so that no human unevenness would add a sideways motion of its own. It began to swing, and the point traced a line in the sand. After a few minutes you could see that the line it carved on the return pass was not quite the line of the pass before. It had shifted, slightly, clockwise. With each full swing, each slow journey of the weight out and back, the shift added up. The plane was turning. The floor was moving beneath a pendulum that was holding still. At the latitude of Paris, the plane of the pendulum turns at a little over 11 degrees an hour. A full circle, one complete apparent turn of the swing, takes close to 32 hours. Watch it for an hour, and the line in the sand drifts by about the width of a hand held at arm's length. Not much, not in doubt. The rate depends on where you are, and that dependence is part of the proof. At the North Pole, the pendulum's plane would come full circle in a single day, because there you stand directly on the Earth's axis, and the whole turn of the planet maps straight onto the swing. At the equator, it does the opposite. The plane does not turn at all, because there you are moving parallel to the axis, and the pendulum has nothing to respond to. Between the two, the rate changes smoothly with latitude. Paris, sitting partway between equator and pole, gets about 3/4 of the polar rate, which is why its full cycle runs to roughly 32 hours rather than 24. That smooth variation with latitude is exactly what you would predict if the Earth is a sphere turning on an axis, and at every latitude where the experiment has since been repeated, the prediction holds. The pendulum confirms not only that the Earth turns, but that it turns as a rigid sphere about a fixed axis, precisely as the mathematics of rotation requires. Foucault had closed something. The search for a direct, physical demonstration that the Earth rotates had been going on since Copernicus, since the heliocentric model first made the Earth's rotation a thing you had to infer rather than a thing you could see. 2 centuries of proposals, failed attempts, indirect workarounds, the slight apparent shift of starlight, the sideways drift of falling bodies, the long procession of the equinoxes. All of these were evidence. None of them let you stand in a room and watch the planet move. Foucault ended the 2-century search with a length of wire and a ball of lead. The year after, he built the gyroscope, a wheel, spun rapidly, and mounted in rings so that it can tilt freely in any direction. Once spinning, the wheel holds the line of its axis fixed relative to the distant stars, because its angular momentum is conserved and nothing is twisting it away. As the Earth turns, the wheel keeps pointing where it pointed, and the mounting turns around it. You can watch the angle between the wheel's axis and the floor change steadily. A full turn in a day. It is more compact than the pendulum, more portable, and in one respect more direct. Still, you can hold it in your hands and feel it resist when you try to turn it. Feel the planet's frame of reference pushing back through a few kilograms of spinning metal. The same rotation that drifts the pendulum's plane and resists the gyroscope's tilt has a larger and more familiar signature, written across the sky in weather. Because the Earth turns, anything moving freely across its surface over long distances is deflected not by a force in the ordinary sense, but by the fact that the ground beneath it is itself moving, and moving at different speeds at different latitudes. A parcel of air sliding north from the equator carries the fast eastward motion of the tropics into regions that are turning more slowly, and so it runs ahead, curving to the side. This apparent deflection is named for the French mathematician who described it in the 1830s. It is why large weather systems do not simply flow in straight lines from high pressure to low, but wrap into the great spirals you see in any satellite image of a storm. In the northern hemisphere, those systems turn one way. In the southern hemisphere, they turn the other. The handedness of a hurricane is a direct reading of which half of a rotating planet it formed on. The pendulum in the pantheon and the spiral of a storm are the same fact at different scales, the turning of the ground made visible. There is a deeper question hidden inside the Foucault pendulum, and it is one physics has not fully closed. The pendulum holds its plane fixed relative to the distant stars. The gyroscope holds its axis fixed relative to the distant stars. Why the distant stars? What is it about the faraway matter of the universe that defines the frame against which a spinning thing measures itself? Isaac Newton thought rotation was measured against space itself, an absolute, fixed stage on which events play out. 2 centuries later, the physicist and philosopher Ernst Mach argued the opposite, that there is no absolute space, and that the inertia of any object, its resistance to being spun or pushed, arises somehow from the combined influence of all the other matter in the universe. On this view, the pendulum keeps its plane fixed relative to the distant galaxies because the distant galaxies are, in some collective way, what inertia is made of. Strip the universe of all its other matter, Mach suggested, and a lone pendulum would have nothing to hold its plane against. The very meaning of rotation would dissolve. This idea that the local resistance you feel in a spinning gyroscope is set by the most distant matter there is was named Mach's principle by Einstein, and it influenced his thinking as he built general relativity. Whether the finished theory fully contains it is still argued over. But the question the pendulum poses is real, and it is humbling. When you watch the floor turn beneath that swinging wire, you are watching the local ground move against a frame that may be set by the whole of the rest of the universe. Both instruments show the same thing. The Earth's rotation is not a convenient description we lay over the sky. It is real, and it can be measured in a room. The plane of the pendulum stays fixed relative to the stars. The axis of the gyroscope stays fixed relative to the stars. When the Earth turns, both devices go on pointing at whatever region of sky they were aimed at when they started, and the planet swings around them. They are, in a concrete physical sense, attached to the rest of the universe, locked to the frame of reference that the distant matter of the cosmos defines. The original weight from the Pantheon was moved to a museum in 1855. It came back to the Pantheon for a time in 1902, for the experiment's 50th anniversary. In April of 2010, the suspension cable snapped, the weight fell, cracked the marble floor beneath it, and was itself damaged past repair. It is gone. A replica has hung in the Pantheon since the mid-1990s, and it swings there now, tracing the same slow clockwise drift in the sand, marking the same rotation it was built to mark. Keeping such a pendulum swinging is harder than it sounds, and the difficulty illuminates what the experiment is really measuring. A pendulum left alone does not swing forever. Air resistance and friction at the suspension point steadily drain its energy, and the arc of its swing shrinks until, after some hours, it hangs still. This has nothing to do with the rotation of the Earth. It is the ordinary death of any oscillation. The signal Foucault cared about is not how long the swing survives, but the slow turning of the plane it swings in, and that turning continues at the same rate, whether the swing is wide or narrow, right up until the motion is too small to read. A short demonstration, of the kind Foucault gave, needs no help. The swing lasts long enough to make the drift plain before it fades. A permanent installation is another matter. To keep one of these pendulums moving for years on public display, its energy has to be replaced as fast as it leaks away, and this must be done with great care. The obvious method, giving the bob a small push each time it passes, is exactly the wrong one, because any sideways component in that push would nudge the plane of the swing and corrupt the very drift the pendulum exists to show. The solution used in modern installations is an electromagnet hidden beneath or above the swing, switched on for a fraction of a moment as the bob passes through the lowest point of its arc, pulling it straight along the line it is already travelling and adding nothing crosswise. The drive feeds the swing without touching the plane. Done correctly, it is invisible. The bob arcs back and forth as though nothing were sustaining it, and the plane drifts clockwise hour by hour, reading out the rotation of the planet beneath the marble floor. This is the quiet discipline behind a device that looks effortless. The whole point of the Foucault pendulum is that the plane of its swing is held by the distant universe and not by anything in the room. So everything in the room that touches it, the air, the pivot, the drive, has to be arranged so as not to disturb that plane. What is left, after all the disturbances are accounted for and cancelled, is the pure signal, the turning of the Earth, written in the slow rotation of a swinging line. There is a detail in the physics of the Foucault pendulum that is easy to step over and worth holding. The pendulum is fixed in the inertial frame, the frame defined by distant matter, not the frame of the Earth, not the frame of the solar system, not even the frame of the Milky Way, the frame of the universe, as far as such a thing can be defined. When that pendulum was set swinging in the Paris basement in January of 1851, its plane was aligned with whatever the universe at large was pointing at, and the Earth has been turning away from that alignment ever since while the pendulum has held to it. That is what the Foucault pendulum demonstrates, at its deepest level, not just that the Earth rotates, but that it rotates relative to something, relative to the large-scale matter of the universe. The replica swinging in the Pantheon is in a sense that is more than a figure of speech, a thread tying the floor of that building to the matter of the cosmos, which raises a question the pendulum itself cannot answer. If the Earth turns relative to the large-scale matter of the universe, what is that matter doing? The pendulum holds still, and the Earth turns around it, but the pendulum is held still by something. It is locked to the frame of the whole observable universe, and the observable universe, is it turning? You are, at this moment, turning, not in any way you can feel. There is no sensation attached to it, no wind, no pressure, no tug. The floor beneath you is perfectly still from where you lie, and always has been, and always will be, whatever you are doing. But that stillness is a local fact, not a true one. The Earth turns on its axis once every 23 hours, 56 minutes, and 4 seconds, measured against the distant stars. At the equator, a point on the surface is carried along at about 1,670 kilometers an hour, faster than the speed of sound. The motion eases as you move toward the poles, because the circle you are being swept around grows smaller, until at the poles themselves it falls to nothing. You have never stood anywhere on the Earth without being in motion at some share of that speed, set by your latitude. Tonight, lying where you are being carried eastward at perhaps 1,000 kilometers an hour by a planet whose turning you cannot sense because everything around you turns with it. That turning is slowing. Not quickly, not in any way that touches a human life, or many human lives laid end to end. But the moon's gravity pulls on the oceans and on the solid body of the Earth, and that pull acts as a brake. The drag is faint. The day is lengthening by something like 1.7 thousandths of a second per century. Atomic clocks precise enough to measure the gap between one day and the next down to a few billionths of a second track the drift continuously. Since the early 1970s, 27 extra seconds have been quietly added to civil time. Leap seconds slipped in to keep our clocks aligned with a planet that is, very slightly, falling behind. The slowing is the long trend, but it is not the whole of the story, and the planet's turning is less perfectly steady than it sounds. Across the span of a year, the length of the day wanders by fractions of a thousandth of a second, speeding and easing as mass shifts around the planet as the winds of the atmosphere strengthen and slacken with the seasons, as water moves between ocean and ice, as the molten outer core slides against the rock above it. Move mass toward the axis, and the planet quickens, exactly as the skater does. Spread it outward, and the planet eases. The Earth is not a rigid top, but a layered, shifting body, and its rate of spin records every large redistribution of its own substance. A severe earthquake, by dropping a great mass slightly closer to the axis, can shorten the day by a few millionths of a second in an instant, a measurable, permanent change in the length of every day that follows. The axis itself is not perfectly still either. The point about which the Earth turns drifts in small circles across the surface, a wandering of the poles by a few meters over a period of a little more than a year, discovered by an American astronomer in the late 1800s, and named the Chandler Wobble after him. It is the free nodding of a slightly non-spherical body that is not quite spinning about its shortest axis, the same wobble you can set going in any spun object that is not perfectly symmetric, scaled up to a planet and kept alive, it now seems, by the restless motion of the oceans and atmosphere, and the slow break never lets go. Run the trend forward far enough, and the day lengthens without limit, the moon drifting outward all the while, until the two motions converge. A day as long as a month, the Earth turning once for each circuit the moon makes, the same face of the planet held permanently toward its satellite. The moon already does this, showing us one face only because its spin was braked into step with its orbit long ago. The Earth is undergoing the same process, vastly more slowly, and the endpoint lies further off than the remaining life of the Sun, which means the Sun will swell and die before the Earth's day is ever truly stilled. The break is real. It simply has more time to act than the Earth has left to be braked. The history of the slowdown is written in stone. There are sedimentary layers, laid down in ancient tidal flats, that record the rhythm of the tides, thin bands of silt and sand deposited cycle by cycle, season by season. Count the bands, measure their thickness, and you can work out how many tidal cycles fell within a year when they were laid down, and from that, how long a day was. In the late Devonian, some 370 million years ago, a year held around 400 days, each a little under 22 hours long. Go back to around 600 million years ago, and the day was shorter still. The early Earth, freshly formed, with the newly made moon hanging close and large, likely turned through a day of perhaps 15 hours, and by some estimates shorter than that. The planet has been winding down ever since, and as the Earth slows, the moon moves away. This is conservation again, doing its bookkeeping. The angular momentum the Earth loses from its spin does not vanish. It passes to the moon's orbit, and a larger orbit is what more orbital angular momentum buys. So the moon drifts outward about 3.8 centimeters a year, roughly the rate your fingernails grow. It seems like nothing. Over millions of years it adds up to a real distance. The moon is farther from the Earth now than it was when it formed, and it will be farther still when the process finally settles, when the Earth's spin has slowed to match the moon's orbit, and the same face of the Earth turns forever toward the moon, the way the same face of the moon already turns forever toward us. That balance, if it ever arrives, is billions of years off. Until then, the spin bleeds away. The moon edges outward, 3.8 centimeters each year, carried by the same law that wound up a collapsing cloud 4.5 billion years ago. The solar system is orbiting too. The whole of it, sun, planets, everything sweeps in a vast path around the center of the Milky Way, at about 828,000 kilometers an hour. Even at that speed, one full circuit of the galaxy takes somewhere between 225 and 250 million years. That span is sometimes called the galactic year. The solar system has made roughly 20 such laps since it formed. The last time the Earth sat at about this point in the galaxy, 250 million years ago, the greatest mass extinction in the planet's history had just finished the end Permian, in which something like 9 in 10 marine species and 7 in 10 land vertebrates were lost. Wind the laps all the way back, 20 galactic years, and you reach a time before the solar system existed at all, before there was a sun to carry the Earth around, before there was an Earth to carry you. None of these speeds is available to any sense you have. You have spent your whole life moving through space faster than any machine humans have built, on orbits of staggering length, and you have felt none of it. There has been no sensation, there is no frame to feel it against. Everything you have ever touched has been moving with you, and beneath even this, there is one more layer. The atoms in your body carry spin. Not the spin of the body turning, not the angular momentum of the atoms jostling around one another. Those are ordinary, classical quantities. This is the intrinsic quantum spin of the particles themselves. The electrons with spin 1/2, the quarks with spin 1/2, locked inside the protons and neutrons. This spin was not picked up along the way. It is not the leftover of any rotation that ever happened. It is something those particles have carried since they came into being in the early universe, in the first fractions of a second after the beginning. It does not decay. It does not slow. It cannot be drained away by friction or distance or time. The electrons in your atoms have had spin 1/2 since they first existed, and they will have it long after everything now turning at the scale of planets and galaxies has wound down and dispersed. The quantum spin of a particle and the orbital motion of a planet are not the same thing. As we have already seen, they share a name and a piece of mathematics, and little else of their nature. The quantum spin cannot be pictured as anything rotating. The planet's orbit can be. What they have in common is conservation. Both are quantities the universe holds fixed unless something reaches in to change them. The particle's spin, conserved since the first instant. The planet's orbital motion, conserved since the cloud began to fall. Both of them, in their different ways, leading back to the same beginning. So, you are turning on a planet that is turning, on an orbit that is turning around a galaxy. Your atoms carry a spin that was fixed before the solar system existed. None of it has stopped, and none of it can be stopped by any ordinary working of the universe. The top on the table fell because friction carried its spin away into the floor. There is no friction acting on a quantum spin. There is no friction acting on the rotation of the Milky Way. Both go on at this moment while you lie here, and they will go on until something from outside reaches in to change them. For the quantum spin, nothing from outside can. The Foucault pendulum in the pantheon is tied, through the plain physics of inertia, to the large-scale matter of the universe. It holds its aim at the stars, while the earth turns under it. The question it raises but cannot answer is what those stars and all the matter strung between them and all the structures they build are collectively doing. Whether the universe, taken as a whole, has a direction. Whether it turns, it is a question serious enough to deserve a rigorous test. And the test has been done. In 1949, the mathematician Kurt Gödel published a paper in a physics journal and presented it as a birthday gift to Albert Einstein, who was turning 70. The two men were colleagues at the Institute for Advanced Study in Princeton, and had been for years. They walked to the institute together in the mornings, talking an unlikely pair, the most famous physicist of the age and the most penetrating logician of the age, keeping each other company on the path. The gift Gödel chose was a solution to Einstein's own equations of general relativity. What Gödel's solution described was a universe that rotates, not a universe expanding outward from a beginning, not the universe we observe, with its galaxies fleeing one another in every direction and its background glow cooling toward absolute cold. Gödel's universe is unchanging, infinite, filled evenly throughout with a thin matter, and it turns as a whole, everywhere at once, around no particular center, the way a rigid body turns. And because it turns in this particular way, within the framework of general relativity, it does something no non-rotating solution had managed to do. It permits closed loops in time. A closed loop in time is a path through space-time that comes back to its own beginning, not a point before you were born, not a point before the solar system formed, but your own past, the same place and the same moment, reachable by traveling forward. Gödel worked out that in his rotating universe, from any event whatsoever, such a path exists. Every point in the universe is connected to its own past by a long enough journey through the future. He cared about this less as physics than as philosophy. Gödel was a logician to the core, and he had spent years thinking about the nature of time. His incompleteness theorems, nearly 2 decades earlier, had shown that any sufficiently powerful system of mathematics contains true statements it cannot prove from within itself, a result that shook the foundations of the subject and has never quite stopped echoing. Now he was making a related move about time. If travel into one's own past is possible in a logically consistent universe, and his rotating solution showed that it is then time as an objective, flowing succession of moments, cannot be a fundamental feature of reality. It would be a feature of our particular circumstances, not of the world itself. It is worth being clear about how strange the thing Gödel found really is, because it is easy to file under science fiction and move on. A closed time-like curve is not a wormhole or a machine. It is a path that an ordinary traveller, never moving faster than light, never doing anything locally peculiar, could in principle follow, and which would return them to an earlier moment of their own life. In Gödel's rotating universe, such paths exist everywhere. The reason this troubled Einstein, and troubles physicists still, is that it sits at the root of causality itself. If you can return to your own past, you can in principle act there. And the clean order of cause before effect, the assumption underneath every physical law we write, loses its footing. Gödel's universe does not break the equations of general relativity. It satisfies them perfectly. That is precisely the discomfort. The theory, left to itself, permits a world in which the past is a place you can revisit. The universe appears to have declined the option, but the equations did not forbid it, and no one has fully explained why reality is as orderly in this respect as it seems to be. This is why the test of cosmic rotation was not an idle exercise. To rule out a turning universe is, among other things, to shore up the ordinary direction of time at the largest scale. And the test was made possible by a particular instrument, a space telescope that spent 4 years from a vantage point well beyond the Moon's orbit, mapping the temperature of the oldest light across the entire sky to a precision of millionths of a degree. That map is the most detailed photograph of the infant universe ever taken, and it is against that map that every model of a rotating or stretching cosmos was checked and found wanting. There was reason to check carefully, because the earlier maps had held a tantalizing oddity. In the first all-sky surveys of that ancient light, some of the largest scale ripples appeared faintly aligned with one another, picking out what looked like a special direction across the whole sky, a pattern that, taken at face value, sat uneasily with the assumption that the universe has no preferred orientation. It was given a half-serious nickname, the axis of evil, and for a while it kept the question of cosmic anisotropy genuinely open. The most careful analysis since has concluded that the alignment is most likely a combination of chance and the unavoidable difficulty of measuring the very largest patterns, of which the sky offers only a few to examine. It has not entirely silenced the debate, but when the full sweep of possible lopsided universes was tested against the best map, the verdict was overwhelming, and it pointed the other way. The universe keeps no special direction. Within a cosmos that holds still, everything else is left free to turn. Einstein found the solution impressive, and was reportedly unsettled by it. He had assumed, it seems without examining the assumption closely, that his theory ruled out such loops in time. Gödel's gift showed that it did not. Gödel's universe is not ours. It does not expand. It has none of the temperature history we read in the background radiation. It does not produce the spread of galaxies we actually see. It is a possibility allowed by the equations, not a description of what exists. But its existence, the bare fact that a rotating universe is a valid solution to the theory, put a question on the table that had not been taken seriously before. Is our universe rotating? Not in Gödel's specific way, but in any way at all. Does the cosmos, taken whole, have a preferred direction? Does it spin? The standard model of cosmology assumes it does not. There is a founding assumption, called the cosmological principle, under almost every calculation cosmologists make, that the universe, on large scales, looks the same in every direction. If the universe were turning, it would not. The expansion would run faster along some axes than others. The background radiation would carry systematic distortions patterns out of keeping with the smooth, near-uniform glow it actually shows. The cosmological principle would fail. For most of the history of modern cosmology, that assumption was accepted without being tested hard. The data fit a universe that looks the same all around. The calculations built on that fit worked, and so the assumption stood. But an assumption that has not been tested is not the same as a fact. In the early 2000s, when the first high-resolution maps of the whole sky's background radiation came in, some researchers noticed features in the data that looked odd, large-scale patterns that seemed to pick out a direction, that seemed faintly to violate the principle of no preferred direction. One such alignment was nicknamed, half in earnest, the axis of evil, for the way it appeared to defy the assumption everything rested on. The anomaly was not large, it was not conclusive, but it was enough to make testing the assumption properly seem worthwhile. In 2016, Daniela Sade, at University College London, and Stephen Feeney, then at Imperial College London, with several colleagues, carried out the most thorough test of cosmic isotropy that had been done. Earlier tests had each checked one specific way the universe might be lopsided, usually rotation, usually about a single axis. Sade's team took a wider approach. They worked out the full mathematical range of ways the universe could be anisotropic, not just rotation, but stretching along preferred directions, shearing. Every combination of these, and calculated what each of those lopsided universes would print onto the background radiation, what temperature patterns it would make, what subtle signatures of polarization. Then they compared every one of those models against the actual sky, using the sharpest, most precise map of the background radiation then available from the Planck satellite. None of the lopsided models fit, not one. The result came out as a probability. The odds that the universe has a preferred direction that it rotates, or stretches, or differs in any systematic way depending on which way you look, were found to be about 1 in 121,000. That was the number the analysis produced. As the researchers put it, you can never rule such a thing out completely, but the chance that the universe singles out any direction over the others now stands at roughly 1 in 121,000. The wider point, the one that made the test matter, is that nearly all of cosmology is built on the assumption that the universe is the same in every direction. And if that assumption were wrong, if the universe did spin or stretch one way more than another, the basic picture would have to be rebuilt. It does not have to be rebuilt. The universe does not turn. Or more precisely, if it turns, it does so at a rate so slow and a magnitude so small that it has left no detectable mark on the oldest light there is, and the odds of any detectable rotation existing at all are 1 in 121,000. Gödel's birthday gift to Einstein described a mathematically consistent possibility. The universe chose not to be that way, and yet, inside that non-turning universe, everything turns. Planets, stars, galaxies, clusters of galaxies, all of them spinning, all of them carrying angular momentum that will persist until something takes it away. And recently it has become clear that the turning runs further out than anyone had ever measured. In 2021, a team led by Peng Wang at the Leibniz Institute for Astrophysics in Potsdam published, in the journal Nature Astronomy, what they described as possible observational evidence that cosmic filaments spin. The cosmic web, the largest scale structure of the universe, the network of filaments and sheets and clusters and empty voids that organizes matter across hundreds of millions of light-years, had been mapped in finer and finer detail over the preceding decades. The filaments are vast, strands of dark matter and gas running between galaxy clusters, some of them hundreds of millions of light-years long, with hundreds or thousands of galaxies strung out along their length. Wang's team used the measured motions of galaxies, drawn from a great survey of the sky, to look for a rotation signal in those strands. The method was the same one used long ago to confirm that galaxies themselves rotate. If a filament is turning, the galaxies along one edge of it should be moving systematically away from us, and those along the other edge systematically toward us, producing a measurable difference in their light, a stretch toward the red on one side, a squeeze toward the blue on the other. By stacking thousands of filaments together, the team found exactly that. The strands were turning, and the strength of the turn rose with the mass of the galaxy clusters, anchoring each filament's ends. The heavier the clusters at the tips, the stronger the rotation. These filaments are the largest rotating objects ever measured, and by tidal torque theory, they turn for the very same reason galaxies do. The same off-center tidal pull that spun up the proto-galaxies in the early universe also worked on the protofilaments. The same mechanism, a scale larger by a factor of millions. In December of 2025, an international team led from the University of Oxford, with Lila Jung and Madalena Tudorache as lead authors, reported a single such structure observed in detail. About 140 million light-years from Earth, they found a thin, drawn-out string of 14 hydrogen-rich galaxies, around 5.5 million light-years long, embedded within a much larger filament of the cosmic web spanning some 50 million light-years. The galaxies were not merely strung along the line. Many of them were turning in the same direction as the filament that held them. Their individual spins lined up with the rotation of the whole structure, like cups turning on a slowly turning carousel. The spin written onto the filament by the early universe's tidal field had been inherited by the galaxies living inside it. The chain is visible here, at the largest scale we can reach. Off-center tidal pulls in the early universe, born of the faint density lumps seeded during inflation, handed angular momentum to the protofilaments. The protofilaments collapsed, conserving it, and became the strands of the cosmic web. The galaxies that formed within them inherited the strands' rotation, modified by the particular histories of their own collapses and mergers, but carrying the original signal still. The universe as a whole does not turn, 1 in 121,000. But within it, rotation runs unbroken from the smallest scale we can measure to the largest structures that exist. And the origin of all of it, the tidal pulls, the density lumps, the tiny departures from perfect smoothness that allowed any twisting at all traces back to quantum noise in the first fractions of a second after the beginning. 1 in 121,000. That is the chance the universe is turning. The universe is not turning. Everything inside it is. There is a wooden top on a table. You have seen one. Maybe you have not thought about it in years. But you know the image, the spin, the hum, the slow list as it loses speed, the fall. It looked like an ending, the spin running out, the object coming to rest. The spin did not run out. It moved. Friction carried it out of the top and into the table, out of the table and into the floor, into the building, into everything the vibration touched, dispersed past any hope of recovery, but not gone. Angular momentum does not disappear. On a frictionless surface, in a frictionless world, the top would be spinning still. Hold the skater beside it. She pulled her arms in, and the spin quickened, and no one had pushed her, and nothing had entered from outside. She drew her mass toward her axis, and the geometry demanded that the rotation rise to keep the product fixed. The spin was already there. It was always there. She did not add to it. She only changed its shape. Now hold both of those at once, the top, the skater, and look again at the fact that the solar system is a flat disk. The cloud that became the solar system was not at rest. It carried a faint net rotation, the gift of the off-center gravity of the matter around it before the collapse began, the same mechanism, working at a larger scale, that gives every galaxy in the observable universe its spin. As the cloud fell inward, the rotation amplified. A cloud hundreds of thousands of times larger than the solar system that came out of it held a rotation too slow to detect. The solar system spins fast enough that its planets have been circling the same star for 4.5 billion years without stopping. The sun was spun up by that collapse and then braked by the grip of its own magnetic field on the disk around it. The spin it lost did not vanish. It moved outward into the planetary orbits, and most of it settled into Jupiter, which is why Jupiter, with less than 1,000th of the sun's mass, carries more than 60% of the solar system's rotation. The sun gave up the spin. Jupiter holds it. The accounts balanced to the last figure. The cloud took its rotation from the tides. The tides arose from the faint density lumps of the early universe. The lumps were seeded during inflation, when quantum fluctuations, the same kind that set the spin of every electron in every atom, were stretched from subatomic size to the scale of galaxies. The line runs from here to there without a break. Leon Foucault hung a wire from the dome of the Pantheon and watched the floor turn beneath a pendulum that held still. The pendulum was fixed not to the building, not to the city, not to the turning earth, but to the frame of the universe itself. The distant matter of the cosmos held it in place, while the planet wheeled beneath. Every Foucault pendulum ever built has been doing the same thing, showing, in a room you can walk into, that the earth turns relative to the large-scale structure of everything. And the large-scale structure of everything, weighed against the finest map of the oldest light there is, does not itself turn. 1 in 121,000. The universe is, as far as any measurement has found, the same in every direction, with no axis, no preferred way to spin. It does not turn. Within it, everything does. The electrons in your atoms have carried spin since they were made, not the spin of anything rotating, but the strange, surfaceless quantum spin, a property they hold the way they hold their mass, that does not decay, does not transfer, does not answer to friction or distance or time. Those electrons were not here when the solar system formed. They were not here when the Milky Way formed. They came into being in the early universe, in the first moments of matter, and they have had spin ever since. They will have it when the last star has burned out. The atoms themselves are in motion. Right now the surface of the Earth is carrying you eastward at something near 1,000 kilometers an hour, depending on where you lie. The Earth is carrying you around the Sun at about 107,000 kilometers an hour. The solar system is carrying you around the center of the galaxy at 828,000. You have moved at these speeds your whole life. There has been no sensation, and there never will be, because to feel motion you need something to feel it against. And every frame you have access to is moving with you. The moon is drawing away about 3.8 centimeters a year, as the tidal drag on the Earth's oceans hands angular momentum from the planet's spin into the moon's orbit. The day is lengthening. The moon is climbing outward. In the late Devonian, the day was a little under 22 hours. 1 billion years from now, it will be longer than it is tonight. The process will run until the Earth's spin and the moon's orbit fall into step, and the same face of the Earth turns forever toward the moon. That balance is billions of years away. Until then, the spin transfers, and the moon moves, 3.8 centimeters each year, carried outward by the same conservation that wound up a collapsing cloud 4.5 billion years ago. What remains unknown is not nothing. We do not know in fine detail how the angular momentum moved through the disk around the young sun. The exact way the field gripped the gas is still being modelled, and the models do not all agree. We do not know whether the backward spin of Venus was set by a single great impact, or ground out gradually by billions of years of tides and atmosphere, or both. We do not know whether there are pulsars turning faster than the fastest we have found. We do not know how fully tidal torquing accounts for the spin of the cosmic web at the very largest scales, or whether something else lends a hand. And there is one question set further back than any of these. The faint density lumps of the early universe were the seed of all structure, all rotation, all collapse, all spin. Those lumps were sown during inflation, and inflation itself is understood in outline and disputed in much of its detail. The quantum fluctuations inflation stretched were already present in whatever field drove it. Why that field had the structure it had, why it produced fluctuations of just that character and no other, is a question that sits at the edge of what physics can presently reach. The chain has an end. The end is a question we cannot yet answer. The top is still, not because the spin is gone, because friction carried it into everything the top touched, and everything those things touched, scattered into the warmth of a table, a floor, a building. On a frictionless surface, it would be spinning yet. We do not live in a frictionless world, but the things that have no friction acting on them, the quantum spin of particles, the orbits of planets, the turning of the Milky Way, those are going on, right now, while you lie here. None of them can be stopped by any ordinary working of the universe. They will continue until something from outside reaches in to change them, and some of them will continue long past the point where anything outside can. Almost everything in the universe turns for the same reason, and none of it can stop. The spin in the most distant galaxy and the spin in your atoms trace back to the same restless beginning. The universe was never smooth enough to be still. Good night.